We are extremely pleased to have Professor Soman Chakravarti's distinguished lecture on graph neural nets and knowledge graph completion. Professor Chakravarti currently is a professor at IIT Bombay and obtained his PhD from the University of California at Berkeley and went on to work at IBM Almaden Research Center, Carnegie Mellon University, and Google. He has published extensively and his work on keyword search databases received the 10-year Influential Paper Award at the ICDE in 2012. He is the author of one of the earliest books on web search and mining. Professor Chakrabarti received several awards, including the very prestigious Shanti Swarup Bhatnagar Award in 2014. He is a fellow of the Indian National Academy of Engineering, Indian Academy of Sciences, Indian National Science Academy, and a distinguished alumni of IIT Kanpur. Professor Soman, apart from these, also comes across as a very avid system administrator on top of several intricate details related to system administration hacks, a hardware engineering hobbyist and tinkerer. Certainly, a multifaceted personality. Well, we welcome Professor Soman for this distinguished lecture.
Thanks very much. I'm delighted to give this talk and address all of you. I wish it could be in person. So today, I don't know how the news of this system administration bit got out. It's usually a guarded secret.
No, I saw it on your web yesterday. And the breadboard, I think the hardware part also.
Okay, so I'm going to talk today about link prediction in two kinds of graphs, in social networks and in knowledge graphs. They have some commonalities and some differences. And in this context, we will look at two problems. One is the issue of collecting representation of nodes from their graph neighborhoods in a way that is insensitive to the order in which nodes are presented to the algorithm. And the second is how link prediction algorithms can become time sensitive, that we are dealing with a graph that's evolving over time and it's not a one-shot thing. This is joint work with Indra, Prachi, Sushant, Abir, and Mosam. For the purpose of this talk, a knowledge graph has nodes which are entities like Barack Obama and Honolulu, and edges which are relations like born in and city of. Now, these knowledge graphs are very, very useful in a multitude of natural language processing tasks like question answering, product search, dialogue, and information extraction. But these knowledge bases are very, very incomplete. Very often, between only 2 and 20% of facts which are actually true in the world are registered in these knowledge graphs. So that strongly motivates the act of looking at a knowledge graph. Yes. Was there a question? Hello?
No. I think I request audience to mute their.
Okay.
Unless if you want to ask a question. Sorry.
Sure. Okay, so these graphs are very incomplete. Most relations are not registered for most of the cases in which they are actually true. So knowledge base completion or knowledge graph completion is a strongly motivated activity. Now, on the other hand, we have social networks like Twitter, Facebook, LinkedIn, or say Archive or Google Scholar, where the nodes are predominantly people, although it could be conferences and papers and organizations too. And then there are various kinds of edges, although not quite as diverse as in knowledge graphs. So Twitter has followers, Facebook has friends, LinkedIn has connections, paper databases have co-authors and citations. Now, there are some similarities and some differences, as I was saying, between knowledge graph completion and social graph completion. Knowledge graphs have extremely rich node attributes. If you look at a well-known entity like Barack Obama, you will find hundreds of attributes. And in fact, Barack Obama would be connected with maybe dozens to hundreds of relations to other entities in the knowledge graph. Now, real social graphs also have rich node attributes to the extent that these online companies can harness your personal information, but not so much in the public domain. And the number of edge types or relations are much fewer. So follow, befriend, post, retweet, reply to, just a handful of them, compared to knowledge graphs which have thousands of salient relations. Knowledge graphs also have very rich temporal attributes. Some events or relations recur, some happen at intervals. There are strong before-after constraints. People have to be born before they become a president and so on. In social graphs, the gamut of temporal relations is again somewhat limited. There would be node arrivals and edge arrivals or deletions, and they have their timestamps, and that's about it. The goals are also slightly different. In case of knowledge graphs, as I have mentioned, we assume that the knowledge graph is very incomplete, and we would like to infer what else we can know from them. Whereas in case of social graphs, we observe the graph up to a particular horizon in time, and then we have to predict what happens after that. Okay, so the motives are slightly different. Now, of late, of course, classic link prediction techniques have yielded to deep link prediction techniques. And in there, the usual strategy is this, that given a graph snapshot, we want to predict what current non-edges are most likely to already be unknown to us or shortly become edges. So this corresponds to recommending new connections in social networks, new citations in scholarly search, purchases in e-commerce, and so on. Now, usually all these algorithms, especially deep algorithms, will compute an embedding or a vector representation for each node from the current snapshot. And these vector representations have to somehow compress the network neighborhood information into a compact vector. Once these vectors are computed, then we can pairwise compare vectors of all nodes and recommend the most similar pairs for linkage. So because this vector and that vector look very similar, the algorithm would recommend the green edge as a new edge that is about to form or should already have formed. Now, so the main core of this technique is the computation of this node embeddings. These are the node embeddings. So how do we do that? And this has led to a whole industry of papers on, starting with graph factorization to node to vec, random walks on graphs, line, GCN, graph sage, and so on. And all of them involve compressing the neighborhood topology into a node vector. So here, for example, is how graph sage does it. It samples a network neighborhood, say at distance k equal to 1, then distance k equal to 2. Then it has this inbound circles of computation. It looks at local features. So these are local features of the green nodes. These are somehow aggregated. So that's like a aggregation function into the blue nodes, which then add on or combine their own local representation and pass it on to the red node. At the end of it, the red node has a vector representation. So how does that look? So as you can see at the bottom, there's this aggregate function which takes all the neighbors of a node U, namely the nodes V, and then look at all their, so this U is a neighbor, and we are computing the representation for V now. So we take all these neighbors and make a embedding HKNV, and that is passed into a concatenation operation with its own embedding from the previous time step. Okay, so from the previous radius or hop. And now we combine it and then apply a linear layer and a nonlinearity to find the representation of V at the kth time step. Okay, so maybe the notation is not quite accurate to the diagram. Maybe K is forward versus backward, but you get the idea. It's a recursive computation. So you fold in from the outside inward toward the red node. Now, of course, the key question is, what should this aggregate be? Now, obviously, the aggregate seems like the aggregate should be ignorant to in what order those blue messages come in. It shouldn't really matter, right? So it should be a symmetric function. But on the other hand, symmetric simple functions have limitations. They can destroy some spatial correlation between the message sent in from one blue node and the message sent in from the other blue node. So in fact, in the original paper, the graph sage paper, they tried a whole bunch of techniques. They tried average pooling, they tried max pooling. So these are by definition symmetry. And they also tried an LSTM on a single random order of the neighbors. So let's say I ordered them arbitrarily 1, 2, and 3, and then I pass them into an LSTM. Now, of course, that would be order sensitive. And if at test time, the canonical order of neighbors can be changed, there is no guarantee that LSTM would work that well. Now, in their paper, they found max pool and LSTM to work better than average pooling. But how sensitive is that? We'll see later in this talk. So there's this dilemma. Either we can design the network neighborhood aggregation function to be symmetric, often just sum or average or max. And in fact, there's a paper by Manzil Zahir and Alex Mola and others, which say that if that network, symmetric network, was given sufficient width, then this could be universal. But in practice, the width required is absolutely astronomical. And in practice, we may miss very valuable spatial correlations. In fact, very recently, Amir Gloverson and his students showed that in this respect, RNNs are strictly more powerful than deep sets, the symmetric aggregators. So the symmetric aggregator is shown in the picture at the bottom of the slide. Now, on the other side, we have this possibility of a non-symmetric aggregation. So we actually plug in the same node embeddings, but this time into some kind of a recurrent neural network, which can therefore remember earlier states and combine the earlier states in some non-trivial way before reading the embedding of the next node. And this gives rise to a much more powerful class of hypothesis functions, which can give a better but non-symmetric node embedding. So this captures correlations between neighbor representations better, which is a plus, but it is sensitive to the presentation order of the neighbors, which is a minus, because an application need not have any guarantee on any kind of canonical order of the nodes. Some people tried to deal with it by averaging over many orders. In fact, even Gloverson's paper suggested that the order sensitivity be addressed by some kind of a regularization. You say, as I change the neighborhood orders, the blue representation here should be relatively invariant if I keep shuffling those nodes around. And Gloverson's paper gave a good recipe of how to limit the search space, but it could still be very expensive. You have to average over many orders of the neighbors, and for large degree nodes, that would be impractical. So we have this fundamental dilemma between the two paths. So we took a third way out, which is we don't try to design a network that's symmetric by design. Neither do we use LSTMs as is and hope for the best by just sampling different permutations of the neighbors. We actually generate adversarial permutations to order. So this is how it goes. So initially, you could think of the recurrent network that we just painted in the last slide as a bunch of node embeddings coming in at the top, like so. Right? So here are the node embeddings coming in. And now there's an identity permutation. It does nothing for the time being. It just passes through each embedding unchanged. And then the LSTM aggregates it in an order sensitive way. Now that gives me a node representation for the center node V, but then there are more gears and machinery. If I'm doing link prediction, I use those node representations to calculate whether a link should be there or not. If I'm trying to calculate the creditworthiness of some person in a social network, that's a node property. And for each of them, there would be some kind of an end task loss. And that would feed back, but we know that this is going to be order sensitive. So instead, suppose this identity permutation can be tailored to order to some non-trivial permutation. Suppose I can change this permutation, and then the red vector comes here and so on. They get shuffled around. And now the same machinery applies. That would lead to a different end task loss. As the permutation network keeps flipping the order, the end task loss will keep changing. Now, this leads to a standard minimax optimization. So here is the end task loss link prediction, which the LSTM is trying to minimize over LSTM's model parameters. But outside that, we want to maximize this over all possible permutation. We want to actually make life hard for the LSTM link predictor. Whenever we think the LSTM link predictor has learned a bit, we say, okay, here's a new googly for you to back to. So I'll change permutations at all the nodes. Now you try out your old LSTM and see how good you are. And turns out the performance of the LSTM will drop. And then the LSTM will try to recover. So the big change is that we are not exhaustively generating these permutations. Instead, we'll do it in a clever way. We will generate exactly those permutations which make life difficult. So we'll maximize over there and only get the maximum, hopefully in time, much less than exhaustive enumeration or sampling of the permutation. So how do we do that? We replace a discrete permutation with a soft permutation matrix. And we do that using a Gumbel-Sinkhorn iterative scaling scheme. And so if you look at the history of deep learning and how people turn soft outputs of a deep learning system into hard decisions, especially ones that are structurally coupled within itself in various ways. In the olden days, when people used to do, say, information extraction or NER, named entity tagging, or relation extraction through CRFs, that used to be a hard labeling scheme with a probabilistic underpinning. But when it came to recurrent neural networks or LSTMs or even transformers, what happens is you get a bunch of logits at the output, right? And then you have to convert the logits into a discrete decision. However, you need to backprop on that decision. And so what's that middle path? The middle path is a softmax. Ideally, you would like to do a max, but since max is not great for backprop, you turn it into a softmax. So a vast majority of deep networks basically use the softmax gadget to walk a tightrope between hard and soft decisions. But now, increasingly, there are other gadgets coming out like the softmax. So for example, in 2016, we worked on soft K-max for doing named entity disambiguation. So instead of just one max, we would like to say K things out of N are switched on, but we want a nice gradient to train everyone. In 2017, we wrote early but not the first paper on using the Gumbel-Sinkhorn iterative scaling, say to match two sentences or finding out if one sentence implies another sentence. And the advantage is that these permutations being soft, you can backprop through these things. So effectively, we have this adaptive sampling of adversarial permutation. And our network, if you start to code this up in Torch or TensorFlow, looks like this. So suppose U is a node to which there's a link from V plus, but there is no link from V minus. So we have one positive edge example and we have a negative non-edge example. Now each node, U, V plus, and V minus have their neighbors. And those neighbors have local features which are called F. Right? So these are the local features of the neighbors or attributes. So those are collected into some kind of a matrix which says, here is the matrix of features of all neighbors of V plus. Here's the matrix of features of all neighbors of U, and similarly for V minus. Okay, so now come the adversarial permutation. So those red boxes are the adversarial permutation generators parameterized on phi. And phi is something we are going to learn through this optimization. So these adversarial permutations are trying to maximize the loss. After which come the asymmetric LSTM aggregation, which is trying to minimize the loss. And after that, with a nonlinearity, we end up with the node representations. Now, once we get the node representation, we have a fairly simple, in fact, cosine-based comparison between XU and XV plus, and we want that similarity to be large. Similarly, we compare XU with XV minus, and we want that similarity to be small. Therefore, we feed that into a standard hinge or ReLU loss, which will start giving a penalty if the bad guy wins over the good guy. If V minus wins over V plus, we are unhappy, and then the loss will go up. Okay, otherwise the loss will be happy. There's also a, so that's a triplet type ranking loss between U and V plus and V minus. And there's also another network called C of Psi, which tries to take XU and turn it into a hash code. And I'll come back to that later on. Because we have to do an all-to-all comparison between nodes in the end, we need a locality sensitive hash in which we'll insert these vectors BU, which will typically be plus minus 1 or 0, 1, so that in the search for the best neighbors of each node, we don't have to look over all n squared pairs of nodes. So this is the whole optimization structure. This is what is coded up in TensorFlow or Torch. Now, how do we evaluate this? So we say a query node is one that is incident on at least one triangle. And that's because it's well known in social network theory that a vast majority of new links are formed by adding this link, right? A to C, if A to B and B to C already exist. So a friend of a friend becomes a friend. We have generalized this in newer experiments to like looking at further hops, and the results are broadly unchanged in character. We partition the neighbors of each query node into train, dev, and test folds. Non-neighbors are sampled uniformly at random if you want to balance, not really balanced as in 1:1, but check out different ratios of positive to negative. And then the system outputs the top k potential neighbors for each query node. Yes, question. Was there a question? Okay, if there is no question.
Request audience to please mute their, unless you really want to ask a question. Thank you.
Okay. Now, at this point, for every node, there are some known neighbors from the training data, and the system proposes these new neighbors to connect to. Based on those, we compute an average precision for this query node and a reciprocal rank for this query node. As many of you know, the reciprocal rank is a little more unstable and sensitive measure, and average precision is much more stable and reliable. And then we can average over these query nodes, Q, to get a mean average precision or mean reciprocal rank. So that's the evaluation protocol. And here are some comparisons at a macro level, but then we'll dig deeper to find more insight. So who are the contenders? There are the classic algorithms, Adamic adder and common neighbor. This is as simple as it gets. You count up the number of common neighbors, or you count up the number of common neighbors with some scaling coefficient. They're actually surprisingly good. We sometimes lose to them, but none of the others. And then there's the first generation of deep models, which use random walks in the graph to compute node vector representations. Somewhat surprisingly to us, none of these are really that remarkable compared to the old classical non-deep methods. Then there's the second generation of graph neural networks. And in fact, we were surprised to see that very often they were even worse than the first generation models. And we scratched our heads and looked very carefully at our numbers and test protocol. And we are reasonably sure that this is the case. And it's not too surprising. If you read graph convolutional network papers, they rarely get any benefit beyond radius 1. And also it is well known that this spatial aggregation is very, very correlation oblivious. So basically GCNs act as low pass filters on the graph. That's the job of convolution in some cases, in the context of graphs at least. And very few second generation graph neural networks can beat the classic or the first generation networks. So we are generally fairly much better. And when we lose, we seem to be losing only to the classic methods and none of the others. But gross numbers are gross numbers. There are two other things to think about. One is the Perm GNN, that is our system method, learning something interesting? And second, can we do it fast? So what is our speed in doing all pairs prediction tasks? So on to the first question. So for example, how does Perm GNN compare with sampling many random permutations? After all, clearly there exists time sufficiently far in the future when you have sampled all possible permutations of neighbors of every node, and then Perm GNN and Multiperm should be identical. And yes, that is true, but it's really far in the future. So this slide shows training time. So as we train and we measure map on the validation fold or the test fold, validation fold, dev map. So as you can see, Perm GNN's map shoots up, hours before or more than an hour before Multiperm can get there. Okay, and sometimes Multiperm can actually never get there because there are nodes with degrees that are too large, and Multiperm must sample many, many permutations compared to the degree to get enough training coverage. Okay. So in that sense, we train faster, although training is not that fast. We have to actually generate these adversarial permutations in a min-max scheme. So compared to that, of course, Adamic adder and common neighbors are very fast. So one may well ask how much value deep learning is adding to this setup. But we have a second, we have a speed advantage as well through our hashing. But before that, we wanted to study further what is really happening to LSTM's training versus Perm GNN's training. So if you think what's going on here, suppose we fix the total order over all the nodes called pi 0. Okay, and we hold that node order to be sacred and unchanged as we are training the system. In those circumstances, one perm or just a single LSTM can reduce loss quite well. It's actually overfitting to the specific order in which the neighbors of a node are being presented, right? So if you have a node V and you have a bunch of neighbor nodes U1, U2, U3, and you're always using the same order to present them to the LSTM, then the LSTM actually gets quite good at tuning its parameters to deal with correlations between them in the best possible way. And that reduces training loss to almost zero. Okay, so LSTM, everyone is at zero if the canonical order is held up. But as soon as we stop the training, we change the node order arbitrarily and we restart training, training loss will shoot up because the one perm or the single LSTM has no idea how to deal with a complete reordering of those neighbors. Okay? And in fact, the training loss goes up, relatively speaking, more and more, the lower is the correlation, the Kendall-Stowe correlation between the new permutation we brought in and the old permutation. So that shows you this upgoing trend. So as the correlation decreases, the training loss degrades progressively. Whereas if you look at both Multiperm and Perm GNN, they're absolutely flat. Okay, so because we are already adversarially or exhaustively generating multiple permutation, we are just not so sensitive to pi zero. We don't care if you change pi zero for a different pi midway. We'll do roughly the same. But as I showed in the previous slide, Perm GNN will train much faster than Multiperm because it's not trying to exhaustively, in a model and data independent way, trying to sample permutations. Okay. Now coming to the scalability part. So as I said before, the similarity between node representations was defined as the cosine between the node embeddings. And the baseline that's used for cosine similarity is the random hyperplane embedding. So I can send you papers offline. It's a beautiful community of work back from the 90s, which designed locality sensitive hash functions, which can bucket similar or close by points in any metric to buckets in the hash bucket space. So you wouldn't have to do exhaustive n-squared computation to find out who the likely other linked nodes, neighbors are going to be. So as you can see, exhaustive takes a long time. And by the way, it's very important to run both tensorized and non-tensorized experiments because a GPU running tensorized similarity computation, like the scoring time, would be very small, as you can see over here. Right? Whereas if you're doing the similarity scoring, the cosine computation on a CPU, you would take a much longer time. However, the blue time is the heap time. This is where we are doing the top K computation. Okay. In case we are tensorizing it, the top K computation starts dominating. However, the overall proportionality is upheld. Exhaustive is very expensive. Random hyperplanes is a lot smaller than that. But Perm GNN's own hashing module, remember that C psi of X, which gave the bit representation B for every node. That was done with an explicit optimization, which tries to distribute nodes evenly across locality sensitive hash buckets. So that really squashes our time down to over an order of magnitude reduction from exhaustive searches for neighbors or likely neighbors, even for graphs of very modest size. And I don't have time to show here. As the graphs scale up, of course, our lead grows to even more orders of magnitude. Okay. So that's the end of the first half of the talk. And this is a good point to take questions about the first half before we move on to the second half, which is about the role of time in knowledge graphs. Any questions? Please feel free to ask.
So there is one question on Professor Soman. You could look at the chat and see if you would want to. And I also have a question once you have answered this.
Sure. Could you ask your question first? Because I might take a second to connect from another place.
So, I mean, I don't normally belong to this area, but we have tried to use this kind of node to vec or node embeddings in the context of robot exploration. And what we have found is to say if a particular object is related or can co-occur with another object. So suppose we want a robot to search for objects in a indoor space. So we we find that beyond one hop, the relations do not really work out. Like, for example, if there are objects in the kitchen, so they would have a high correlation with kitchen objects, but they would not have a correlation with the exploration. And what we have found is, hello.
Yeah.
I mean, like, I don't know how, I mean, does your Perm GNN and layers relate to that somehow, or is it a common thread in GNNs? Because we use it purely as a black box and we don't know how to get into it. And yeah, so, but this is something which we see, like we are not able to build a relation, or we can't say like an object in the bedroom would be 2 hops away over a lot of training data from an object in the kitchen. When we train it across diverse environments, like in robotics, a lot of environments in habitat, and they have synthetic computer vision environments. So
right.
I was wondering, like, if this, what you're saying, has any correlation, or can we plug in any of your layer and see does it make sense to do something?
Not yet,
like
I think.
Yeah.
Yeah. So Perm GNN's goal wasn't to necessarily push the frontier of number of hops. It was more horizontal, right, to deal with the correlation across neighbors.
Okay.
Now, coming back to the application area. So typically when people talk about, say, robot movements or computer vision, MRFs have been so successful there precisely because of the M, because we believe that it's Markovian at a certain order, right? And if you believe that there is no second order correlation in a 2-hop path in a house, then that's how it is. If you believe there is a correlation, but a GNN or GCN is not being able to catch it, then we need different gadgets to deal with it. And there are starting to be some of those. For example, so this is much more to find path-based features in paths or depths longer than one. This is very common in knowledge graphs because of the normalized nature of the relationships. So for example, someone is born in a city, that's 1 hop. The city is located in a state, that's 2 hops. The state is a part of a country, that's 3rd hop. And therefore the person is a citizen of the whole country. Right? So clearly, multi-hop path inference is quite critical in knowledge graph relations like these. Right? And for example, you could even have, if someone is an employee of a company, but the company has 10,000 employees and the company was set up 20 years before the person joined, then the probability of the person being the CEO is very small. Right? Whereas if a company has 10 people and this person has been with the company from the beginning, then obviously the probability of being a CEO is larger. So knowledge graphs give a much richer playing field for these longer path features. And the way people have to deal with it. So William Cohen has done a lot of good work on this. They have something called a path rank algorithm. So the idea is you have to get rid of your single hop Markovian assumptions. And you have to build this contrastive path features. So someone who is a CEO, someone who is not a CEO. You describe shorter but not hop one paths and try to build discriminators between whole paths with global scaling, rather than assuming there's a probability normalization at each hop. Right? So that's where things seem to be going. And yet another place where this multi-hop reasoning is very important is nowadays question answering. So if you ask, so in fact, that's an active area where I'm very interested, which is if you go to Google today, or if you ask Google too many times, they'll learn, they'll fix it. But if you say, go to Google and say, who was president of US when the moon landing happened? You'll get an answer. But if you say, who was the health minister of Tanzania during the year that the moon landing happened? It's structurally a very similar question, but they won't get it. At least not as of 2 days back. Now, what you want to do is to decompose the question into saying in which year did the moon landing happen, and then who was the health minister of Tanzania in that year. So that's another example of multi-hop features being important in doing the eventual scoring. But traversing knowledge graphs or answering multi-clause or multi-hop questions is really a huge field, and that would take us far out of today's talk scope. But yeah, I'd be happy to talk to you offline about it.
Oh, sure. Yeah.
Okay, now I can see the question from Deepti. While computing the node vector, how many hops of neighborhood should be considered? Right. So as I said, we are still prey to GCN-like situations. If we take 2 hops, it hardly adds any value. So how can we differentiate between 2 nodes connected to the same set of neighbors? Local features. Right. Local features is one. The other technique that's often used is the Westphaler-Lehman node numbering, so WL numbering. You can Google it and find out the algorithms to do that. So these are like topological labels which can be attached to nodes through a simple traversal algorithm, and that disambiguates basically the position. So if the nodes are completely symmetric with regard to the remaining graph, then there's no hope, right? Then you have to depend on other features, like maybe these nodes are people and they have age and place of birth and features like that. So those kinds of things start off the recursion, and then the structural recurrence proceeds along these paths converging on the red node at the center. Then you do that for every node as the red node in turn, and then you start comparing their vector representations. Does that clarify things a bit? Okay.
Yeah. So
great. Yeah. Very good. So now we can proceed to the second half. Yeah. Then it depend on other features, like maybe these nodes are people and they have age and place of birth and features like that. There's a long echo. I hope it doesn't continue. Okay. So the second half of the talk is about temporal knowledge graphs. So real knowledge graphs do not only have these timeless or eternal relationships, but they also have times associated with them. So Barack Obama was president of the US only in a range of years, and in some other range of years, George Bush was president, and so on and so forth. So everything passes with time. This too shall pass. Now, traditional knowledge-based completion represents each entity and every relation as some continuous geometric artifact, like could be a vector. But you could interpret these continuous representations in various ways. You could regard E vector as either a point in space, or it could be a rooted vector starting at the origin and ending up in the tip E, and so on. Meanwhile, the representation for R could be a vector which can be interpreted as a displacement to apply to an entity, to move it to some other place. Or R may not be a vector, it may be a matrix that projects the original E vector to some other vector. Or R could be a rotation. You apply it to an entity, it rotates into a new position. Regardless of that, the mental picture is that your knowledge base completion system is a box like that, the box in the center, where representations of the subject, relation, and object go in, and the belief that subject, relation, object holds in the knowledge base comes out as output, right? Of course, if you're thinking of time, then time would go in as an additional item into the input, and we have to calculate the belief, okay? Now, usually what happens, so as one example, there's the so-called trans-E model, which is translate an entity, trans-E. How so? So we take the subject and we apply a displacement corresponding to the relation. And if we land up near the object, then you have large belief that SRO holds in the knowledge base. For example, so this actually descended from Word2Vec, where people found that if you take man and you add a relationship vector R, you get king. And if you take woman and you add the same relationship vector, then you get something close to queen, right? So this relationship vector, roughly speaking, confers hereditary leadership onto people. It makes king out of men and queens out of women. Now, when the incomplete knowledge graph is given to us, we train these entity and relation representations using the known but incomplete triples. And then we apply back this model on the graph to infer these unknown triples. And over the last 5 or 6 years, this has led to literally hundreds to thousands of papers with various variations of this box. In principle, you could say any universal network deep enough and trained enough will implement this for you. But in practice, as usual, humans still have to occupy a central role in understanding how subject, relation, object, and possibly time interact, and design the shape of this yellow network so that the belief comes out right. And over the years, this has led to a bunch of innovations. Currently, some of the leading models are complex, which uses complex embeddings for subject, relation, and object, and a host of others. We don't have time to go into them. We'll only look at one or two in what follows. So in temporal KB inference, there will be two tasks, and these are somewhat new. These are somewhat modified from the usual knowledge-based inference, which is just adding new edges, relation edges between entities. So a temporal table looks like this. It has subject, relation, object, and the time. And I'll fully admit that we are only scratching the surface now, and we characterize time as either an instant or an interval or a repeating series of time points. So for simplicity in this slide, let's say that Obama was president of US in the range 2009-2016. Now, what is link prediction in this setting? We will provide the begin and end time. We will provide the relation, and we'll provide one of the subject or the object, and we'll ask for the other. So we can say Barack Obama was president of which country between 2009 and 2017, and USA would be a positive answer, and India would be a negative answer. Similarly, when the subject is hidden and the object is shown. There's also the new task of time prediction. So here we specify the subject, relation, and object, but we keep the time secret, and you're supposed to guess what the time is. Now, this sounds like a very difficult exercise unless I know other things about Barack Obama from training data. Right? I mean, if Barack Obama and USA were entities in a vacuum, then how could we possibly answer it? For example, if we know that US has other known presidents from -infinity to 2008, we will never think of plugging Barack Obama in there because experience has taught us that usually countries don't have two or more presidents at the same time. Right? Meanwhile, if we knew that Barack Obama was born in some year, say 1950 or something, 60, then we know that he couldn't have been president before that, or even when he was 10 years old, from experience in the knowledge graph. Now, even the best systems, like complex embeddings and derivatives of it, fail in some spectacular ways in this. So we took something called T-complex, temporal complex embeddings, which I'll discuss in a minute, and gave it this training data where there's this triple, Shin Era is married to Cha In-pyo from 1995 onwards. And then the test fold query said, Shin Era was born in which year? And this recent method, TNT complex, said 2013. So of course, a human would never, ever commit this mistake. So what's going on, right? So how did TNT complex try to combine those four signals, and can we do any better? So here's what complex does. Complex takes the subject, relation, and object entities and relations, and each is embedded to a complex vector. Now, they take the complex conjugate of O, and then they do this three-way inner product. So sum over dimension, subject D, relation D, object conjugate D. That is what is this inner product. And then they take the real value of that as the confidence in the score of this, this relationship. Now, the question is, when time comes, how do we introduce T into this? And TNT complex chose the easiest way out. They just made a four-way click out of it. So sum over D, SD, RD, O conjugate D, TD. T itself had a whole complex vector dedicated to it. And that we also do. Okay. So TNT complex was supposed to be better than complex, and yet we saw the kind of mistakes TNT complex can make. It can make people get married before they're born. Right? Now, we started thinking more carefully about the interactions between these four artifacts, S, R, O, and T, and we decided that S, O, and T should have their own intrinsic vector embeddings, but R should become a multifaceted thing. So I'll justify why. So we now create three representations for R. The R representation which judges how compatible are S and O directly without respect to time. And then whether S can participate in that relation at time t and whether O can participate in the relation at time t, as I was justifying with Obama's lifetime and US's lifeline as well, right? So, and this then lets us create these things which are like potentials in graphical model terminology. So there's a potential between RSO, which is a vector, and S and O. There's a potential between RS and T. There's a potential between RT and O. And finally, there's a fall-through potential between SO and T. Okay. So this is the TimePlex base. We have more to follow, the base scoring function. And if we draw it, it sort of looks like a complicated organic molecule. This is 2021, and we're all worrying about molecules, right? So that's what our function looks like. But that's not all. As I also mentioned, there are various explicit constraints between two relations in time or a single relation in time. So history may not repeat, but it rhymes, as someone said. Winter Olympics, with rare exceptions, will happen every 4th year in various places. Barack Obama was born in 1961. He married at the age of 31. He entered Harvard, was in an educational program in 1988, and 20 years later, he was elected the president of the US, perhaps his highest achievement. Meanwhile, Einstein married at the age of 24, and between finishing school and winning the Nobel Prize, he spent 28 years. Again, between being educated and reaching highest accomplishment in life. So you see that there's some soft pattern here, right? People do marry at different ages, but it doesn't vary that much statistically. Similarly, people's delays from education to positional accomplishment also satisfy some relatively predictable distribution. So can we exploit these things in addition to the base model that we had? So to make this more concrete, what kind of temporal constraints are we talking about? So there's this fact recurrence and fact non-recurrence. Olympics games do recur. Country elects president in a recurrent pattern. Events are held regularly. Whereas a person is born exactly once and dies exactly once. It never recurs, right? Except for some strange characters that we will not consider in this talk. So by the way, that picture really dates us. Whoever recognizes that picture, it must be at least 40 years old. So now there's also ordering between relations. You have to be born in order to die, and this guy also violates that rule. But anyway, so now there's also this time gap between relations. People will typically die some 70 years after they're born in a normal world. Okay, so how do we mine these? How do we fold this back into our TimePlex model? So we can start by collecting a whole bunch of relation pair time lags. So we can say Joe Biden was born in 1942, Joe Biden graduated from somewhere in 1965, and the gap therefore is 23 years. Meanwhile, Michelle Obama was born in 64, graduated from Princeton in 1985, the gap was 21 years, and so on and so forth. Once we collect those, we can build, again, I'm not claiming we have a beautiful universal theory here. Just for convenience, suppose we have a simple normal distribution of the gap, right? If you know there's a one-sided constraint that one thing cannot happen before the other, you can, of course, truncate one side of the normal, if you will. In any case, in this case, you could say, even assuming it's normal both-sided, which is not correct, of course, you get a mean of, say, 22 years. Right? So people typically graduate at 22 years. And this gives you a distribution, and we can also fit a suitable standard deviation. If there's not enough information from the training data, sigma is just going to be very large. Now, if someone asks, how likely is it that Obama was born in 1961 in the test phase, the system will say, well, let's see what we knew about Obama from the training phase. If we found that Obama was graduated from Columbia in 83 and he became president in 2009, that gives a certain probability mass to his being born in 1961. So each of those known facts with their times will give a certain evidence through this normal distribution to the candidate, which is 1961. Right? And then finally, these scores will be aggregated, and out will come a score for the candidate 1961. Right? Recurrence works fairly similarly. How do we know, or what confidence do we have that there was a presidential election in the US in 2016? Well, that depends on nearby years in which it was held. if it was held in 2008 and 2012 and 2004, what we have to do is to look at this candidate and look at the closest year where it happened, right? And the closest should follow a reliable distribution, probably with a very small, sigma, if the event is really truly recurrent, right? So the nature of the model is the same. It's just that in the relation pair constraint, we have a model of mu, which is dependent on a relation pair, and standard deviation, which is dependent on a relation pair. In case of recurrence, it's of course purely between a relation and itself, right? So this is a typo. So it's mu r and sigma r. These are different mu's and sigmas for the recurrence bit. Okay. So that defines the full model. First, we have the TimePlex base model plausibility defined by those S, O, T, and the 3 R embeddings. And then we have the plausibility from the recurrence model, which depends on mu and R, which are indexed on a single relation. And then we have plausibility from relation pair time gaps, which are of course predicated on or indexed on a pair of relation IDs. And these three combine to form the TimePlex score. We can compare that against the goal to find a loss. And now this loss will backpropagate along all these arms and train all these parameters. In practice, we do a careful curriculum where we first stabilize those 6 embeddings, and then we start training all of them together. Okay. Then the recurrence model, and finally the relation pair model. And things are free to drift a bit then, but the one set is relatively stable at that point. So it's kind of common sense that, you realize that you already have a time-less knowledge base steady, then it's easier to calculate what's going on with the time-based parameters. So that's how we train the TimePlex system. Now, surprisingly, even evaluating these is not very well established. And earlier papers which were trying to evaluate temporal knowledge base completion made certain mistakes, which made their estimates either too pessimistic or too optimistic. And the crux is, what if a train fold revealed a fraction of the valid interval during which what if the training fold exposed a bit of the information that's asked for in the test fold? So, for example, if from the training fold I already knew that, say, someone was CEO of a company up to this time, and the test question is over here, then up to this time I already know the answer, and I should not be given credit for this part. Whereas if I predict this correctly, then I should be given credit for only that part. Okay, so this was not being accounted for correctly, and in fact, the training and test folds were overlapping in earlier studies, and we have redone their evaluation to be more fair. Okay, so and how does it go? So with our corrected evaluation functions, we find that we are better than complex and TNT complex, the 2 best known numbers before our times, across 4 fairly diverse knowledge graphs or event databases. Now, how about the time interval prediction performance? This is even more tricky. So suppose the gold interval during which a relation holds, I'm talking simply in terms of intervals, you have to think separately for recurrent events and things like that. Suppose there's this gold interval which is shown in gold, and then the system predicts this blue interval, and there's this non-empty intersection. Then we can give credit which is proportional to the intersection, or maybe proportional to the intersection over union. This is IOU, which is also frequently used in computer vision. But that has a problem both for training and evaluation, that if the intersection ceases to be non-empty, the intersection becomes empty and there's a gap, then that just reaches 0, and that doesn't help anyone, right? I mean, there are zeros and there are zeros. There's a 0 where the system and gold are almost touching, versus 0 where the system and gold are far apart, in which case you are even less happy. So to correct for this, we propose these all vowel evaluation measure called AEIOU, which is affinity enhanced intersection over union, has all the vowels exactly, which is max of 1, where 1 represents the minimum granularity over time, and the intersection divided by the hull. So the hull is not the union of system and gold. The hull is the smallest convex region which contains both system and gold. So that does penalize you for the gap. And this is a generalization of IOU in that it tries to maximize the intersection, but it also tries to maximize the distance when the intersection is 0. So, and with respect to this, and we have shown that AIOU actually satisfies some nice axiomatic properties, which IOU does not, and that's in our paper. Now, with AIOU measure, as you can see, we are quite a lot better than TNT complex, and definitely complex, which we don't even show here. So all this is fine. So there is a numbers section of the paper, and you get great numbers, and that's why your paper gets accepted. But that's not enough. And what is the insight, right? So deep systems are notorious for not giving insights into how things are working. So, and this is how we try to dig out a couple of details. So first, do the time embeddings mean anything? Recall that we have a full-blown embedding for every time point. So we fix a year. So we do embedding at a granularity of whole years. And then we compare the embedding of the fixed year with the embedding of all the other years. And on the x-axis, we actually plot the difference in years between the two vectors. And on the y-axis, we plot the L2 distance between the two vectors. And lo and behold, as the difference in year increases, the L2 distance also increases. This is something that we absolutely did not include in our loss objective in any way. In spite of that, miraculously, it turns out that distant years are also more distant in L2 space. So that gives us a lot of confidence that our time embeddings are actually somewhat meaningful. Even better, going back to that case where TNT complex said someone was born before they married. Let's take x-axis as time, and on the y-axis, let's design based on TimePlex's predicted score or confidence. Let's try to convert that into a probability by suitable scaling and plot some kind of a relative probability measure. It's not between 0 and 1 or directly comparable to any other probability, but just as a relative measure as to how strongly we believe that Shin Era was born in various years. And remember, the gold was 69, right? And as you can see, we predict 67, and that's where our peak is, right? So that peak is 1967. But the important thing is that we have this very clear, bias toward the correct region. So we know that some years are extremely unlikely given what else we know about Shin Era. But as TNT complex, despite throwing in the T vector into their four-way inner product computation, has basically no clue. Its probability is flat across the whole spectrum of time. Right? So clearly, our time embeddings are not only meaningful from a metric perspective, but they're also helping us make fairly sharply peaked predictions around or close to the correct value if we know other things about either of the entities participating in the relation. So to conclude, link prediction or graph completion in the wild is very, very far from pure mathematical artifacts like low rank matrix or tensor factorization. We have node features, we have edge labels, we have edge features, we have network neighborhood that gives you clues, we have time, and all these have to be folded in. And there is still an ongoing quest for better models than just pure mathematical abstractions. And in this talk, we took two small steps. We learned how to aggregate neighborhood information better, being permutation invariant, not as a provable thing, but we are trying to make things more permutation invariant by adversarial training, and that's the Perm GNN work. And then we showed how we can model edge times in knowledge graphs more carefully so that we can take into account relative time displacements between relations affecting a single entity, or that certain relations or events, rather, they recur in time, and can we use their other occurrences to drive our predictions. Okay. As a quick vignette of other work we do, I'm very interested in open information extraction, and we have done a bunch of work on new grid-based, transformer-based labeling strategies for doing open information extraction from text. We are very interested in domain adaptation and generalizations of deep models. So deep models are notorious for being very confident even when they're wrong and when their input data is actually quite unfamiliar. So can we prime them ahead of time? One work I particularly liked was our ACL 2019 work on adapting word embeddings from gigantic pre-trained models. So nowadays, because only a few organizations can afford gigantic training resources and data resources, people are in the habit of downloading models and code from one of these big companies and then plugging it into their code. But how do you know that given the corpus workload you have, that those embeddings are at all appropriate? On the web at large, potential may have a dominant meaning, which is someone's potential to become a leader. Whereas if you look at physics Stack Overflow, potential means a very technical, narrow term. So if you're using word embeddings inherited from somewhere else, you might get it wrong. And we show that various post-factor transformations is not enough. You actually have to try to go back to a genetic corpus and do an attention-based reselection of word vectors. I'm also interested in complex question answering, as I hinted in the middle of the talk, that today question answering systems have come a long way, but they are still terrible at solving multi-component questions. So if you say, who was Barack Obama's father? And then you ask, suppose the name of the person is ABC. So you say, how did ABC die? So it turns out today that when people design these multi-hop question answering benchmarks, they were not careful enough, and 3 years of research happened on it. There are BERT-based excellent QA systems which would get complex queries like, how did Obama's father die correctly? And then you go back to them and ask, oh, by the way, who was Obama's father? And then it would get it wrong 40% of the time. Right? So without knowing who was Obama's father and without any corpus passage directly mentioning how Obama's father died, the system somehow manages to give you the right answer, but it's not robust. If it's getting it with some magic, then you're not sure it will generalize to how did Indira Gandhi's father die. Right? So it's very important to be able to decompose and compose, and humans do it really well. And AI-driven QA systems are still reaching there. I'm also interested in privacy in social network link prediction. We have a recent paper on that. If you are friends with smokers and bungee jumpers, and a health insurance provider gets to know that, they might bump up your health insurance because you're keeping bad company, right? So you might decide to hide those links from LinkedIn or Facebook or Twitter. On the other hand, there are these link prediction algorithms which are trying hard to fill in incomplete links. So if the link prediction algorithm is doing its job, even if you hide the fact that you're friends with bungee jumpers, maybe it can be found out, and then your cover is blown, right? So can we get most of the benefit of link prediction while protecting sensitive links like that? So we have some differential privacy results along those lines. And I also work in social network buzz or chatter prediction. So how do you observe a very short prefix of an initial tweet and the perpetrators, and then you make a prediction as to how popular that tweet is going to be. And this is important for engagement prediction and advertising, and even catching fraudulent behavior, like things deviating from that kind of normative model. So I gratefully acknowledge support from all the usual suspects, and I truly thank you for your attention to the talk, and I'll be happy to take final questions.
Kamal has a question, please. Kamal, you may want to unmute and.
Hi, Kamal. Good to talk.
Okay, hello, hi. Couple of questions, first question is, there is this whole work on lineage and data provenance and everything, wherein since the birth of some piece of data till its consumption at the end, there is a fairly good record that is kept and is used. This is first part of and how that relates to your TimePlex kind of a work and all that. This is one question. The other question is, if you went back in, say, 1990s, early 1990s or late 80s, and say, how do you do inference? People will say, okay, but you build a prologue system with facts and predicates, and then run queries on that, and then you get that. And when I look at your examples, I feel that at least for avoiding large number of silly mistakes, a prologue-oriented inference system might work either for pre-processing or post-processing the results. And has it been tried?
Okay, I'll answer your second question first. So certainly Tim Rocktaschel and Stephen Rydell and others have been looking at unifying the logic world with the embedding world. There are some networks with universality proofs in restricted settings of inference, where they show that things which can be done through logical inference can also be done with these deep embedding systems. So there's definitely a lot of interest in that, putting together the symbolic reasoning with the soft reasoning part. So far we have not bitten into that community yet. But to some extent, the temporal constraints are like a soft judgment of that with a specific structure. So I totally agree with you that an integration might lead to further gains. The trick, I think, is to find out exactly where the softness should apply and where it shouldn't apply. To give you a more trivial example, for at least a couple of years, information retrieval researchers were trying hard to beat, say, things like BM25 scoring, passage scoring, with deep passage scoring. Because after all, we know BERT is infinitely wise and it knows all. So why bother with the information retrieval engine anymore? I take the query, I append the candidate passage to it and ask BERT if the passage is relevant or not. Job done, right? And that didn't work for a little while. And people are very surprised as to why it wasn't beating BM25 scores. And then they found that a query needs to be softened and hardened very selectively. So if you say tourist attractions in Hyderabad, you really do mean Hyderabad. It will not do if you instead say reported tourist attractions in Warangal, right? And so that's where the query is hard. Okay, you don't want a softening of the query in that. But instead of tourist attraction, if it's like places to see, you want a softening there, right? And the same applies in different forms to symbolic or structural knowledge inference as well. You may want to soften, say, someone's date of birth a little bit if you're not sure, or when they graduated from, or when they attended a particular university. But you may not want to soften certain other hard constraints, like which town they're born in, right? So one problem with these unified models has been that they cannot easily go heterogeneous. They cannot easily judge where to be soft and where to be hard. And that may be a good frontier to work on, but I'm not really an expert in the logic world, so that's about as far as I can go. In response to your first question, which was about provenance, data provenance. So yes, there's a lot of work on data provenance. I don't remember, Jennifer Widom and others in the late 90s. And I think that's a little different from the knowledge graph setting I'm talking about, because provenance is about how a particular data was recorded into the system, right? What was the source? What is the reliability of the source, and so on. Whereas what we are talking about here is that the source could be anything. It's just that the knowledge graph has relation edges which are qualified by points or intervals or recurrent intervals of time, saying this relation only holds at these specified times and not at other times, right? It's not when that data was acquired per se, but what the state of the world is at different points of time. So that seems to be a little different. Does that answer your question?
Yeah, yes, that's fine. Yeah, okay, great, thanks.
Any other questions?
Can I ask?
There's an echo.
So my question is the following. You have this system for, say, knowledge-based enhancement, knowledge-based completion kind of tasks. Now, if you are looking at sources that are outside the knowledge graph, then, for example, maybe another knowledge graph, or even open data knowledge that is available in a structured and unstructured form, maybe in the form of web, and so on. What are your insights that, can you offer certain insights where knowledge-based completion tasks benefits from the external knowledge graphs or even the web?
Okay, so that's also fairly established. There's a bunch of smaller research projects which may not be so individually remembered, but Google had this VLDB paper some years back on their data vault project, which is like a gigantic mashup of structured and unstructured sources, and then reconciling entities across multiple sources, like what is a particular universal product code from Amazon is the same as this Wikipedia page, which is the same as this Freebase node. So we first merge those. And similarly, we can try to merge relations and types, and then we scrape web tables and random web pages on sites to get additional information about those. So it's like everything goes into the kitchen sink, and more structured knowledge comes out. So Knowledge Vault is probably like the distillation of, I don't know, 10 person-years of work inside Google into a 12-page paper, which of course doesn't do justice, and there's no code, of course. But you can find bits and pieces of it in academic projects for which code may be available. So there have been grand unification projects like that, typically in industry, where they had to build. And Amazon has its own knowledge graph project. Microsoft, as you might know, also has Satori and so on. Increasingly, people who started with non-product knowledge graphs like Microsoft want to get into product knowledge graphs, and Amazon wants to do the converse because they want to pick up what outside people are saying about their products in the form of other entities in reviews and quantities in reviews and stuff like that. So certainly unification between unstructured text and knowledge graph is very old business, starting with, say, entity linking right down to like opinion extraction. So what do people say about the newest Samsung phone, right? So you try to detect mentions of that phone in text and then do sentiment analysis around it. So that's fairly well established. In terms of reconciling multiple knowledge graphs, similarly, so Knowledge Vault includes that. And we're also doing work on, say, taking product-oriented knowledge bases and integrating that with generic knowledge bases like Wikidata. So then the usual questions, right? How do you know that this node is the same as that node? And there's a fairly sizable research literature on that too. So you build node embeddings from both sides, and then you compare the node embeddings across the two sides. Just like we're doing within the same graph, you do it across multiple graphs. There's one work called BERT-int, so interaction model with BERT, where they actually apply BERT to the textual description of various nodes, and that is already very, very strong, especially if it's a multilingual BERT. You can now integrate Wikipedia in different languages, right? And then they add a little bit of salt and pepper to it and get a few more percentage points by looking at, again, neighbor-to-neighbor matching. So, Perm GNN may also have something to do there. So we are looking at some of that. You are basically known by, who you interact with, right? So for years, questions of what is your identity has plagued not just philosophers, but government departments alike, like national ID and stuff like that. But at the end of the day, who you are comes down to asking 15 people around you what they know about you, right? So identity is entirely situational and contextual. Yeah.
Thank you.
Any other questions?
Any further questions from students? I think you can raise your hand and ask.
Or you can type in the
you can just I think intervene, and I think this is open to all. Anyone can ask. I mean, through audio.
So if you have any questions for the future, which might occur to you later, feel absolutely free to email. I'll be very happy to answer your questions. If you want to try out the code, I can share that with you as well.
Yeah. If there are no further questions, may I request Dr. Ravi Kiran to, conclude the talk. very hot, very, what is seems to be like an intractable problem of distilling knowledge from the data out there, and making predictions spatially, temporally at one hop level with permutations and multi-hop over time. It's not so much my area. So maybe Ravi, if you think you can thank the speaker, it would be great.
Sure. So this is the second time I'm been listening to Professor Somen's talk. And one thing that strikes me is that even if you are out of the domain, there are nice nuggets which you can take away. And in this talk, particularly the last couple of minutes, which Professor Somen spent covering some of his other work, I'm sure was well worth the wait for others who may have felt, whether they were hanging on too long enough. But I'm sure the wait was well worth it. So I really wish to thank Professor Somen in this regard, and hope that there will soon come a time when he can visit and give a talk like this in person to a full house here at IEEE.
I would love to do that. I would love to do that.
Yeah, we would certainly hope, that you could come sooner. I'm hoping that the pandemic does get over very fast. And I think we request you to visit all the research centers. And I'm sure, like, at least broadly, this graph neural nets, I think, is popular across areas. People use it sometimes just for, with profound understanding, sometimes with very superficial understanding. And maybe your presence here and interacting with students would help, at least to know whether we need to use sometimes these networks at all, or are we modeling the problem, are we barking up the wrong tree, or are we really on the right track? For someone who has been in this area for so long and who's widely recognized on this planet as a foremost researcher in this area, we would really love to have you here, Professor.
As soon as possible and safe, yes.
Thank you.
And conversely, I would love to host some of you at our department here. And it was a real pleasure addressing all the students. Please feel free to come to me with questions. I'm very happy to chat. Okay.
Sure. If there are no further questions, so maybe we can have this, session temporarily end. I think there are a lot of things. At least, maybe perhaps I would like to ping you as well after a couple of weeks, if possible, on what we are going to do, and see if something can happen there. Yeah, thanks.
Thank you for.
Eden, would you like to say something?
No. I just want to thank Somen. I was listening with one ear all through. Not that I understand this so much, but thanks for giving this talk. And yeah, hopefully things will be. We all wish for better interactions, but this is better than nothing. So
yeah,
I hope the students found it well. Yeah. So thank you.
Oh, my pleasure. Absolutely my pleasure. Sure. Goodbye.
Bye.
Thanks a lot. Thank you, Professor. Thank you. Thanks everyone for coming. Yeah.